Thank you for joining this webinar hosted by SIGRE Canada. My name is Kasun Samarasekera. I'm currently the NGN Technical Lead for the SIGRE Canada NGN Exec Committee. So, before we start with the webinar, the technical webinar, I'd just like to explain, who we are. So, the Next Generation Network, or the NGN, helps bring a new generation of power system professionals into the world of SIGRE and help deliver a platform where early career professionals can feel comfortable sharing their ideas, get an opportunity to interact with industry experts, and get involved in SIGRE working groups and technical events. Our mission statement is as follows. SIGRE Canada's NGN aims to support the next generation of Canadian power system professionals by providing them with opportunities for technical growth, networking, leadership skills for students and young members. So, with that being said, the SIGRE Canada NGN is happy to host this technical webinar on the design and implementation of master power plant controllers for stability studies. So it's my pleasure to introduce Tamajit Chakraborty. He is a senior engineer at Electrical Power Engineers based in Austin, Texas, specializing in renewables such as onshore and offshore wind, solar, battery energy storage, and hybrid plants for interconnection studies for several different ISOs in North America, including ERCOT, PJM, HECO, ISO New England, CAISO, and even Australia, AMO. He's previously been with Siemens PTI and Mitsubishi Electric Power Products and has an extensive experience in custom model development of electrical equipment in both RMS PSSE and electromagnetic transient PSCAD software. Mr. Chakraborty works closely with several developers and OEMs to develop their user-defined models to represent their dynamic response and meet local grid code requirements. He also works in performing special electromagnetic transient studies for NERC mod studies for equipment model parameterization and power plant model validation to test data. So it's my pleasure to hand it off to Tamajit, who will start this presentation. And if you have any questions, we will have a question and answer period at the end of it. So please just wait for the end and we can have a kind of a discussion and question answer period after. So Tamajit, I'll hand it off to you.
Sure. Thanks, Kasun, for the very kind introduction. First of all, I'd like to thank you and the entire SIGRE NGN group for inviting me. It's my pleasure to present here, and thanks for having me. So, as Kasun said, what I'm going to present today is mainly on the design and implementation of master power plant controllers for several studies that we have done here at EPE. Some of the work that we have done here is an outcome of the projects that are, at the site, and based on experience and working with several stakeholders like the renewable developers, OEMs, and working as a consultant is always you get to get to see the both end of the spectrum. So some of these experiences, I would like to share with everyone up here. So feel free to, stop me at any time if you have any questions, and I'll try my best to answer them. So, I'll just get started by saying that even before we go into master power plant controllers, we will have to, at this point of time, talk about hybrid power plants, right? Now, the reason for that is hybrid power plants are becoming extremely, popular across the world, not only across in North America, but in several other regions. We're seeing that, AC coupled or even DC coupled BESS with wind and battery, or solar or PV and BESS are getting very popular. Now, from our point of view, a hybrid power plant, I've put the definition up here for everyone. It's basically termed as a resource that can comprise of multiple generation technologies, right? Which are controlled as a single entity. So naturally, what happens is as more and more inverter penetration goes on, the challenges as studies engineer or as a transmission planner becomes quite difficult. The reason for that is, the conventional power systems that have been designed are based on synchronous machines, and with more renewable energy penetration, we are seeing a different sort of, controls with different technologies and different vendors. They try to achieve kind of the similar thing, but they have different type of controls that they have set up. So they try to achieve the same goal, but in different ways. As a result, we see several, dynamic responses which are, I think, very key to understand and study when we are performing, simulations in the software. So this is actually where, master power plant controllers become very important as they need to be developed to control these entities as a single resource behind the point of interconnection from a transmission planning point of view, and also, from site-specific point of views. So in this work, what we have done is we've built several master power plant controllers that are developed in both RMS and EMT platforms to study the dynamics of such plants in order to better understand the nature of such resources. So having said that, it's always important to understand what sort of models does a studies engineer have in the available software toolkit. It could be either a generic open source vendor neutral models, which are available in any commercial transmission planning software tools like PSSC or RMS, or PSLF here in the West, and also parts of ERCOT, where TSAT is also a tool that is developed by PowerTech Labs that are used. Now, in case of site-specific projects where it is recommended by the OEMs that you need to use user-defined models. Now, the reason is why. It's very simple, saying that, okay, we can use the generic models. Now, can the generic models give you a trend of the response that you can get from the user-defined models? At sometimes yes, sometimes no. So naturally, the go-to option is the user-defined or the user-written OEM models, which are typically developed by original equipment manufacturers that aim to closely represent the equipment's physics in the real world or in the operating set. Now, I'm no way saying that one is better over the other. It's just that we have to use our engineering judgment in order to understand which models should be used. Both the generic models as well as the user-defined models are important. And the end user also has to understand the limitation and the application set of either set of models. Now, I'll show you in a later slide where we have done some work where we show that a generic model for some conditions can actually be parameterized and tuned to represent an OEM specific model. However, in some cases, the OEMs might come and say, okay, the generic models are much more simpler, as a result of which it cannot be represented. So naturally, there is a sort of engineering judgment that one has to use when they're doing simulation studies. So what we did internally here at EPE was we have several OEM models that we have benchmarked as generic models. This is just to show that, if you see the slides, the plots up here for different, network tests, for, let's say, lagging power factor, LVRT, or, HVRT, and then a power frequency response or a voltage step test. What I'm trying to say is, we actually parameterize the site-specific OEM models to the generic available software models, and we can see that, okay, within a reasonable percentage of error for different operating conditions, this is not just for one test, we can get some sort of a very clear or a very close response. Of course, it's important to note that different models have different nuances and different tricks. Some of the OEM models, like say, for example, this is a very nice, plot which shows that in orange, you have the user-defined model, and in blue, I've plotted the standard library model, where you see there's some sort of oscillations when the, the inverter models are entering and exiting right through, because the generic models, of course, doesn't have hysteresis built in there. Now, with hysteresis in there, with the OEM models, as you can see, it's a much more clear transition from the VRT mode to the steady state value, after the fault is cleared. So it's also very important to understand that, yes, the generic models can be tuned to represent the OEM models for some sort of conditions, but not always. But can we get very close response? Yes, we absolutely can. However, it's also very important to understand that we do not end up, tuning parameters in, either sets of models to just make, the orange plot look over the blue plot, right? It's important to know which parameters are actually translated in the field on which are user tunable, right? So, for example, a good standard would be the inertia constant of a synchronous generator, let's say, just as an example, where you cannot tune that in your study because it's something which a physical mass that is there in the rotor, right? So it's very important to understand and spend some time that which parameters are actually tunable and which parameters are, of course, limited to the actual physics and actual, tangible uh, stuff that is not allowed to be changed. So having said that, what we did is, and I wanted to show this here to the audience, that it really comes down to the fact of the availability of the models. Your simulation results are only as good as the models that you have and as the best that you can parameterize and tune. So having said that, what we did was, this is an example of a MOT 26 and a 27 study for a 420 megawatt of a solar plant in Texas containing, like 135 solar inverters from one particular OEM. This is an example in which we actually developed working with the power plant control supplier. We wrote down the control architecture and wrote down the source code of the power plant controller in PSSC. And we can see that after we did the testing in the field, you'd kind of see that both the measured and the simulated values in the simulation plots are quite close to each other. It shows that this OEM user-defined model, as well as the power plant controller that we wrote, a kind of a very similar response. It gives kind of very similar response. You could argue that could get closer, but there is actually no set of industry requirements, at least as to my understanding in North America, where it says, okay, this much percentage of error is acceptable or this much isn't. But even some sort of responses like here, if you see for the reactive power in orange, you see the transformer is probably tapping, and we could still have a dynamic model in PSSC for an OLTC, and we could still do that. But having said that, this more or less gives a good understanding that the simulated models in the software and the testing that we did in the field are a close match. Sometimes, for example, I wanted to show you another, project where we had a 200 megawatt of wind plant in Texas that, consisted of, wind turbines in particular OEM. So sometimes, as consultants, what we do is we work with the OEMs directly to validate the response. And there is a lot of back and forth between developers, ISOs, and the other stakeholders involved to make sure, and which is very important, what is there in the field should actually be present in the simulations. Otherwise, the simulations are useless. It has to represent the physics of the equipment that are there in the site. Now, this particular, project is a good example of that, where we actually obtain the power plant controller's parameter dump file directly from the OEMs. And we confirmed that the PSSC simulations for the NERC Mod 26 test are one of very close to each other. So if you see the states test and the simulation results in the orange and blue, they're very close to each other. Now, does this mean that we only use user-defined models, or we only use generic models? Of course not. in my working, I've seen we have seen sites where we require dynamic power compensation, where sometimes the wind turbine generators are in a slave mode or they could be in a master mode. Now, what happens in such cases is if let's say the wind turbine generators are in either mode with the available toolkit of the models that are there in the PSSC library, uh, and I'm strictly speaking about PSSC here. I'm going to talk about some of the PSCAD simulations also in the later slides, is you do not have, a model that could represent, let's say a power plant control. So what should we do in such cases? So in those regions, what we do is, we develop the source code working with the, uh, power plant controller supplier. To, we sit down with them, develop the block diagram architecture, and then we write the source code of the PSSC, and we make a PSSC user-defined model in Fortran. For example, very recently we encountered a site which was quite interesting, where a custom power plant controller was needed, where we had to coordinate between multiple devices. And not only that, it was required in order. So this particular site, it was mandated that there was one particular, wind turbines, and there was a STATCOM for dynamic power compensation. And, the STATCOM is also able to control cap banks. However, the control philosophy of the site was that it was mandated that MPPC, or the master power plant controllers, when it commands any response, first of all, the wind turbines has to provide the queue based on their capability. Then the dynamic VAR device comes into action, and finally, if required, the dynamic, VAR, in this case, the STATCOM, switches on or off for capback. So, for such specific sites, which are site specific, sometimes it's not always possible. It's not always available in the PSSC, model library, and in such cases, you have to define, or you have to develop user-defined models. So, having said that, though, we have also done studies in, for NERC Mod 26, where this is a great example actually, where we have obtained close match to test data using the generic models as well. And you can see there were multiple units which had to be controlled by one power plant controller. And if you see the, states test and the simulation results, they're very close to each other. So what I'm trying to say here is I'm not, preaching that one model is better than the other, or this should be used over the other. But what I'm trying to say is, based on the project, specific particular project, and the example that we have, or based on experience and the available toolkit, we need to make an engineering judgment on which models are important. Of course, there are different control philosophies for different sites, which may not always be represented by generic models. In that case, we'll have to go to user-defined models. Now, having laid that ground on, what I'm going to now talk about is some of the controller design issues that we have seen in our course of the projects. This is a good example of a forensic case study that we did for a particular client, where we investigated the root cause of wind turbine generator stripping due to uh, AVR tests in ERCOT. We found out that the latency of the tap changes, which are mechanical, and the AVR, which is electrical, also plays a huge response when it comes to simulating such complicated controls. So what we did was, in this case, we used PSCAD as the preferred software platform, because PSSC would be unable to capture some of the responses. And the OEM mentioned that their PSCAD model is the closest replica of their product up in their site. So what we did was, we actually modeled the longest feeder of the site, which had several wind turbines. And we actually, if you can see, the simulation and the test, we tried to first see what was the reason for the turbine to be testing. And this is where I would say that being optimistic is important, because if you have to make sure of the models that you have actually are giving the response that has actually happened in the field. First of all, what you have to do is you'll have to first, replicate the event for such forensic analysis. Uh, this is important because, the coordination between, slow mechanical parts, like I mentioned, the load track changes and the VAR controls, in the AVR for the OEM becomes important. So having said that, I'll give you a few examples of some of the master power plant controllers that we have developed here at EPE. This is a good example where we have a 300 megawatt of wind plant in Texas, and the interesting part of this project was this was very complicated design because if you see, it has three different OEMs and the turbine types for one particular OEM is different. So if you see, there are like 4 collector systems. One OEM, one has wind turbine generator variant 1, which is there in the first and the fourth collector system. The second collector system has a mix of turbine. So you see, there is a different OEM. There's a third OEM as well with a different variant. And then there is also the first OEM's wind turbine generator variant 1. Similarly, what happens is in the third collector system, you have 2 different OEMs yet again. So naturally, the problem in such projects is the fact that if you all have one control point, which is the high side of the main power transformer, what's going to eventually happen is the PPCs between the OEMs are going to fight each other. So what we did for this project, or the strategy that we took, was we actually in our project we modeled like dummy lines where it's a jumper or a zero impedance line, and each of the OEMs have their respective power plant controllers that can monitor the medium voltage side rather than the high voltage. So this was the design of the plant, right? So each of these, so you can understand like each of the OEM PPCs are monitoring their respective medium voltage collector systems. On top of that, what we did was we actually developed, once again working with the manufacturer of the power plant controller, we sat down with them, understood the control philosophy of their RTAC system that is there in the site, and then we wrote the source code of the master power plant controller. Now, why is this important? This is important because of the fact that the control philosophy was like this, for fast events, let's say in case of like, larger disturbances like faults, the master power plant controller is effectively blind to that event, right? So what happens is the master power plant controller will only provide a coordinated response in slow events like a voltage step or a reactive power step events. And for faster events, like let's say fault, kind of responses, each of the individual OEM PPCs and the wind turbines are going to respond with their own. So it had a complex, outer loop control that sends the command to the respective OEMs, which were all working in a slave mode. So basically, what happens is there is a group control logic, which is shown in this diagram, where the master power plant controllers basically feed the commands to the respective PPCs for slower events. And for faster events, it's basically blind. So now the question is, why is it blind? The reason is that the MPPC actually has a timer and a deadband by which it, refreshes itself and monitors the voltage at the high side through a timer. And the latency of the timer is around 1 to 2 seconds. So naturally, what happens is for a faster event, let's move my slide around here. For faster events, it's basically as if the master power plant controller is actually blind to that event. Now, the master power plant controller has 2 modes. One is a voltage droop control, which is shown in this diagram, and also it has a reactive power, Q control. How the Q control is working, and presented that in a slide, is it's important to note that with such complicated controls, which you have almost 7 different wind turbines, and on top of that, you have a master power plant controller. 2 things are fundamentally important. Number 1 is parameterization, and number 2 is the effectability of the models. So the effectiveness of the user-defined models that are used in this project becomes extremely important. So you see, I've plotted the step changes in reactive power, and it's kind of more or less, visible that the MPPC is able to achieve a response in a coordinated fashion amongst the wind turbine generator OEMs. Now, one of the other concerns that we had for this project was this disconnected in an area which had low short circuit strength and is in a place of a weak grid, so effectively short circuit ratio of less than 3. So this MPPC also had to take into account of such network conditions for this particular project. So what happens is, during the design, we got to know that the master power plant controller can send Q set points as an algebraic function between the desired fraction of the difference between the Q that is sensed and the Q that is going to send it. So basically, if the explanation of this particular plot is that if you see, let's say 40 mVAR has to be commanded by the master power plant controller, how the plot is read is in the x-axis you have number of steps, and in the y-axis is the Q command. So let's say the Q command is 40 mVAR. So if you want a faster Q injection, you would set the step size, to be 2, which means that going from 0 to 40 would take, around like small time, compared to if you have a weaker grid, because you have to inject Q slowly, otherwise, the voltage is going to, bounce around, and the dq to dv is going to be pretty high, and it's going to result in instability, and also the PLLs or the phase lock loops of the wind turbine generators are going to get messed up with the control instability and the known phenomenon of weak grid issues that a phase lock loop faces. So if you have a higher step size, you can see that you can still command 40 mVAR, but it takes a different amount of time, which is kind of what I would say is a better response in case of a weak grid. So this was something that we developed, and we also wrote the model in PSCAD. At a first glance, as everyone can see, this is probably not a very good benchmarking per se, but here, as you can see, blue is PSCAD with red is PSC, and I've plotted the reactive power and voltage from one particular OEM and the point of interconnection, reactive power and active power. Now, I would like to first of all say, it's very important to first acknowledge and understand the difference between the software platforms. One of the tendencies that I've seen here in North America, at least, is, we want to see plots on top of each other without considering, engineering judgment. So what I'm trying to say here is, we all stakeholders, the person who is doing the studies, the consultant, the OEMs, the ISOs, and the developers all need to work together hand in hand to understand basically the difference between the simulation softwares, right? So of course, fundamentally PSSC and PSCAD are different. Yes, benchmarking is required to understand if the models match across the software platforms, but with such a complicated structure, it's it's difficult, I would say, to get a very close match, but it's doable. And I would like to say that this is nowhere the finished product yet. This is a part of an ongoing work that I am doing here at APE, and I hope that I'll have a better match soon. But it's very important to understand that the complexity behind the control logic, not only for the wind turbines as well as the power plant controllers, but also from the OEMs. For example, from one OEM confirmed that the PSSC and PSCAD model is identical. We still don't know between the other two OEMs. So there could be a lot of unknowns and differences across the two software platforms that could cause such a difference. So what I would like to say is the last point is the noticing and understanding the differences is very key when you're doing a simulation, rather than understanding like why is it different, how is it different. So we all as an industry, I think we all stakeholders have to work together on understanding the differences and then work towards and provide a technical solution or a scientific explanation on why there are differences and what can be done in order to mitigate, or if they're explainable. Now, moving on, this is a different project where this is a hybrid plant which I was involved with designing in Hawaii, which had located PV and BESS. So as you can see, there is again one particular OEM provided the BESS and the PV both. In this case, both were user-defined models, and we were contacted by the power plant control supplier to develop, the models for this particular site in order to meet the requirements of Hawaii Electricity Council, which is also called as HECO. So the primary purpose of the master power plant controller, like any power plant controller, is to regulate and control both the PV and the BESS in a coordinated fashion, and also achieve closed loop control utilizing the feedback from the POI. There were different control modes, like for reactive power, there was voltage, power factor, and then there was this QV droop functionality, kind of similar to what was shown in the previous slide for the other project. So we actually wrote the source code in PSSC to achieve this size specific functionality. And then we also consulted with the OEM personnel, the PPC, as well as the inverter personnel, to tune parameters in order to meet the grid code requirements. Something very interesting came up. That's why I have this particular slide, which I want to explain up here. So as you can see, this is a design issue for a power plant controller, not only for hybrid plants, but I would say for any plants. So whenever there is like a voltage right response, an important aspect is that we should have the PPC designed in such a way that it freezes the reactive power P and the Q command. And also not only this, which is based on voltage. So let's say, for example, when the voltage drops, let's say beyond 0.85 or 0.9, it enters the right through mode, the PPC should freeze itself, right? And not only that, it's very important to understand why we should have anti-wind up of PI controllers. So this is one very interesting case that I found out in my simulation studies while I was writing the source code and doing the simulations simultaneously. Is if you see the picture here on the left, the plot here is the terminal voltage, and the plot here on the right is the reactive power of one of the particular inverters. So you see, once there are stages of voltages that are simulated or played back at the POI bus for a voltage profile based on this particular ISO. So you see the region up here is once the inverter comes up or comes out of LVRT mode, what happens is this particular PPC did not have an anti-wind up, right? So what was happening is if with this particular QV droop up here, you translate a Q command into a voltage, and then you take the difference between the reference voltage and this particular voltage that you come from the droop calculation, pass this to a PI control. But if the PI control does not have an anti-wind up, what happens is, and also if it does not have these functionality, situations like this can arise. So in this case, what had happened is once the inverter comes out of the LVRT mode, the plot here in red is actually right on top of each other of blue till this point. So as a result, what happens is the PPC had actually kept on accumulating this error, right, when it was freezed. And because the error into the PI controller, the integrator, was not flushed to zero, what was happening, once this inverter came out of LVRT mode, it sends a huge Q command. Now, what happens is, as a result of this Q command, the inverter, once out of VRT mode, now has to follow the Q that is commanded by the PPC, which is right up here in the simulation. So as you can see, the reactive power shoots up, And the reactive power shoots up in such a way that and what happened was it triggered the HVRT mode. Once it triggered the HVRT mode, it stays there because of the HVRT gains and other parameters up there. So the point which I'm trying to make is these are some of the important things which I call it as a FRT mode toggling. And these are some of the controller design issues that we have to take care of when we're designing master power plant controllers. So it could very well easily try to understand VRT for LVRT mode, but then suddenly it gets HVRT mode triggered. Now, this is one of the projects, moving on, which we did for, one particular client in Australia was this is a hybrid plant that is contained of both wind and BESS in conjunction, right? So once again, we have different OEMs, different control technologies trying to achieve the same thing, and then you need a master power plant controller that can coordinate the responses between the units. So in this particular case, we developed both the PSSC and the PSCAD user-written models. And the point which I want to illustrate up here is the complexity arises because of the different technologies, and the models that we receive from OEMs are black box, right? So only when you talk to, or the manufacturers, they will try to give you a response which you understand it better. As I said, we all as stakeholders need to work together. But this is one of the nicer ones where we actually were able to, tune the power plant controller, response with this particular project for both PSSC and PSCAD. And as you can see, uh, the the red is PSCAD, blue is PSSC. We have plotted the reactive power, active power, at the voltage at the POI. There's a typo up here. It should be reactive power instead of P. This is the active power, and the voltage. As you can see, a very close match who is able, we're able to get a very close match between the two softwares. So I'm not saying, from my previous, slides that yes, there are complexities associated. So we have to apply our engineering judgment to understand when and how we can, get close match between the software simulations. But yes, this is definitely possible. Some of the other things that I wanted to talk about is regarding the design. Sometimes I've seen how a couple of different parameters that have been set in the models actually lead to instability. This is one good example where we see that instability arises because of triggering nonlinear controls and changes in control mode. So the plot which I have plotted up here is the wind turbine generator voltage and the reactive power. Is we put the high voltage right through profile for ERCOT, and what was happening for this project is this particular OEM, the PPC was designed in such a way that it will be able to extract maximum reactive power based on voltage deviation. So if it sees a voltage deviation, of more than 2%, what it does is it sets a very aggressive, QV gain. What basically happened was if the PPC is not configured properly, what happens is as soon as you get out of VRT mode, if the PPC is not set properly or if the PPC is too aggressively tuned, instabilities could arise. So what was happening in this case was as soon as the wind turbine generators was out of the VRT mode, they try to get back to pre-fault state. And in order to do that, it tries to go back, what was the scenario before the fault. As a result, what was happening, the terminal voltage, as you can see where my cursor is, it goes beyond the HVRT threshold, right? As soon as it goes beyond the HVRT threshold, a cyclical triggering happens where again, you try to bring down the reactive power. And then once again, out of VRT, you again, the wind turbine generators go beyond the threshold and it triggers again. So we discussed this with the OEM, and they said that the PPC was not correctly set up at their end, and they had too aggressive QB gains. And after discussing and consulting with them, we realized that the gain of the the one of the generators and the PPCs were not set up properly. And once we tuned it, you can see a much more better response. So this is something that can happen in studies where I call it FRT mode cycling, which is in red, versus the intended operation, which is in blue. So these are some of the design features that that can happen in case of master power plant controls, or rather any power plant controllers. I almost This is my second last slide, so I hope I'm doing good on time. This is one of the interesting projects that we did very recently, where we actually developed a power plant controller for a grid farming resource. Now, grid farming, as you know, is becoming very popular in the industry, but apart from Great Britain, who are writing a grid code, and part of FICO, where they have requirements for grid farming, there is not a industry consensus yet of a proper definition, and grid codes haven't been updated yet. It's coming, but it's not updated yet. So I've tried to define this based on several examples that I've seen across the industry. Is that an inverter that can change its current injection in response to a transient event, and also has black start capability, which means it can be able to provide a locked voltage and frequency for other grid following inverters to latch onto, is probably called as a grid farming resource. Now, having said that, we did this work in Puerto Rico, which is an island, and we wrote a PPC with advanced grid functionalities for a particular manufacturer, and we integrated that, with this grid farming model. Now, I'd like to say up here that this particular resource, grid farming resource, is a grid-connected grid farming resource, and it cannot yet work. The technology is there, but the models that we developed are not yet ready for an islanded mode of operation yet. So just point to let you guys know that this is a grid-connected grid farming inverter, in which it is actually basically a virtual synchronous generator. So you can see with if we play back like a frequency, you see like the inertial response similar to a synchronous machine. And then the same thing can be observed, for a grid connected mode, it's try to support the voltage in response to the PPC that commands the voltage change at the PI. So once the voltage goes down, the grid connected grid farming tries to support the grid. So as I said, the grid codes in the world are mandated only for grid following as of yet. Yes, it's coming. Grid farming inverters are becoming the need of the hour, which have been presented in several forums, but grid codes are not updated yet. So this was my more or less the last slide, but I wanted to provide some key takeaways and some of my future thoughts that I wanted to share. So in by no way or means I'm saying that one model is better over the other, or the generic library models or the user written models, but I'm trying to say that the end user, the simulation engineer, has to make the right judgment and take the call before performing simulation studies. Both are equally important, and both are needed in the industry. With more and more hybrid plants, master power plant controllers are becoming extensively popular, and site-specific functions are there for particular power plant controllers, which are more or less, I would say 95% or 90% of the time, you need to develop user-defined models, because the generic models do not provide that functionality. We also have seen projects where recently has a win in conjunction with grid farming BESS. So these are coming, and it's going to be a challenge. And unless and until we have right models, we'll not be able to study such projects. More or less, I think I like to close with the final thought, saying that there will be differences across simulation platforms. It is possible to get a similar response, but at the same time, we need to understand and spend time on understanding differences between the plots across platforms, different platforms like RMS and EMT, And despite real code compiled models, which are now the standard for PSCAD OEMs, there will be differences. And as a simulation engineer, we need to understand when performing studies what's the difference and how is the best we can mitigate that. So with that, I'd like to hand it over to Kasun. That comes to the end of my presentation. Kasun, and this over to you.
Thank you so much, Tamajit, for a really, really interesting presentation. It's a lot of material you covered there, and we really appreciate you taking the time to create these presentation slides and share this information with everyone. Thank you so much. And with that being said, if anyone has any questions, please feel free to either unmute yourself or you can write a message in the chat, your question in the chat, and I can ask it to Tamajit. Yeah, but feel free, let us know if you have any questions. I'm sure Tamajit is eagerly ready to answer it. So give some time here. Let me see if let me just go through and allow the mic if people want to unmute themselves here. I think. Oh, we got a question in the chat there. So the question is from Matthias. How do you implement the algorithm for the PPC in PSCAD or PSSE?
Okay, so I'll try to understand the question first from Matthias. When you mean by algorithm, are you asking about the control structure, the block diagram? So in that case, what we have done is we actually sit down with the power plant control, manufacturer, and we try to understand what the block diagram looks like. So of course, I understand that the block diagram sometimes it cannot be translated into a simple blocks be given the complex functionalities in the model, but we try our best to translate the controls into sort of a block diagram and then develop the source code in PSCAD or PSSC. And then once we develop the source code, we actually integrate that with the inverter models and then write that in both PSSC or PSCAD using Fortran and then simulate it. If I understood your question correctly, Matthias.
So Matthias is happy. So we got another question from Marshall James. When you set out to model the MPPC in PSSE, how do you determine if you can use plant BU1 model and multiple REX BU1 as opposed to writing your own UDM?
Great. It's a great question, actually. So note that the PLNT BU1 can only talk to the REAX3 or the REAX4. It cannot talk to any other models because the var commands that it sends, the way the model is written in PSSC library right now, it can only interface with the REAX3 or the REAX4. So I'll go back to this example here. So let's say, yeah, this could be a great example. So let's say you have a generic model. I'm just saying for the sake of James' question. If let's say you have a generic model that can represent this OEM BESS and the PV, right? There can be two things up here. You could use the REAX4 BU1 and then the PLNT BU1 can send the commands. However, note that there are several power plant controllers that have different control strategy to the generic power plant control. The REPCA is absolutely similar to the PLNT BU1 except that it has one extra parameter. So there can be two things. If you use generic models and you can see that the PLNTBU1 kind of represents your power plant controller, then go ahead, you can use it. However, the complexity arises in case of two things. What if your PLNTBU1 does not represent your PPC? In that case, you have to write your UDM. And secondly, if this is a user-defined inverter model in itself, you cannot use the PLNTBU1 because the PLNTBU1 can only integrate with the REAX3 and the REAX4. So in that case, you have to write your own user-defined model. Does that answer your question, James? Okay, perfect.
All right, we got another question here from Mandala. When working with the OEM to model the user-defined controller, does the OEM provide the IP information about the control architecture, or would you be working off a block model?
So it's a great question again. It's more has got to do with legal stuff rather than engineering. So no one shares their IP. Pavan. So no, they don't share the IP information because it's their proprietary controls. So what we do is we sign NDAs, and we roughly try to understand their controls and translate that into a block diagram. Now, the block diagram kind of represents their PPC. But yes, to your point, no one shares the IP information about the control architecture. So at the end of the day, there are several things that are there in the PPC that may not be required to capture in the user-defined models, because it's known when the plant has been commissioned and designed that it's based on one particular working mode or one particular control mode. So you can work with the OEMs to translate their controls into some sort of lead lag blocks, PI controllers with dead bands, and then come up with a block diagram.
Okay, so do we have any more questions? Please post it in the chat, or feel free to unmute yourself. You could also just ask that way. We have a couple more seconds if anyone wants to ask more questions.
I think Pavan had a follow-up question on what's the allowable percentage difference, if at all one exists for every ISO. It's a great question, actually, for the difference between PSSC and PSCAD. So as of now in North America, I am not aware of any percentage of difference, but based on our experience and working with different ISOs, what I can confirm to you is a certain percentage of error of 3% to 4% is kind of acceptable for NERC mod studies. So you see, for example, for measured and the simulated values, you can see that 3 to 4% is acceptable. Now, when it comes to PSSC versus PSCAD, one engineer, who's reviewing, your submission could easily say that, what, even if the POI, active power and the reactive power at the OEM matches at the terminal, you do see a difference, of maybe more than 10% in, in the response. So yes, we have to understand the difference. It's not always that you will have the red plot over the blue plot, but it's important to understand that what percentage of error can be done away with. To your question, there is no particular standard as of yet. It's kind of the trend of the response. And also what's interesting to note is it depends on the person who is reviewing. So there is no standard yet, but I would say if I had to take a fair share of, from my experience, I would say 3 to 4% is kind of an allowable percentage difference that I have seen is acceptable between both the platforms.
We have another question from Marshall.
Mm-hmm.
Is there a way to quantify how close a standard library model must match the UDM model? Is this also 3 to 4%?
I think it's a great question again. As I said, I'll refer to my slides up here. So we took a user-defined model. We've actually taken several OEM models and tried to replicate the response. Now, when it comes to quantifying a dynamic model, there are two things that we have to understand in great details. One is, was a dynamic response for a very large event and one for a smaller event, right? So in case of, matching the standard library models to the user-defined models, I would say, let's say, for example, the IEEE 421.5, guide, that's a good one to refer up here, because of the simple fact, and I've put this in a footnote, that, for example, if you take the static exciter, which is the library model in PSSE, the static exciter ST4C, that is basically a Basler DCS or an Eaton or an Emerson static exciter system, right? What I'm trying to say here is this ST4C can represent Basler as well as Eaton or Emerson. In the same way, for certain operating conditions, you can have, not for all, and there is a caveat to this, not for all conditions, but for some conditions, some operating conditions, you can have the generic model to be a close match with the user-defined model, but not always. And what's the difference? As I said, I always, try to ask this question myself. I would still say 3 to 5%, but let's say in case of this, what difference does it actually make if this, if I just zoom this out a little bit, what difference does it make, you have difference between this or this, for you? It's not the end of the world, right? So what I'm trying to say is, or for example, this is a good example maybe for us, smaller, disturbance are kind of similar. However, for a faster disturbance, you could argue that, okay, there is a difference. So again, it depends on the simulation engineer and the person who's reviewing, but a good rule of thumb maybe would be less than 5% is or should be, an acceptable response.
All right, so thank you so much for your questions here. These are all great questions. We got a question from Curtis. Thanks for the great talk. Do you have any recommendations for reading materials for young EITs or engineers looking to learn more?
I think it's a great question actually, and I would say that it would be experience that would help everyone who's especially doing simulations. Unfortunately, there are not many uh, available resources up online that would help you. But what could be helpful is which is one thing that I try to say is, if you try to read more research papers, journal papers, that's something which would be very helpful to understand this. But to your question, Curtis, I think this is more from an experience point of view. So the more you do, the more you dabble, and it's like video game. The more you play with the toy, the more you try to enjoy, or the more you try to understand it. So I think it come from experience of doing more and more studies, or dabbling more with the softwares.
All right, we've got a couple more questions, Tamajit. I know we're going a bit over here. Are you okay to go a couple more questions?
Yeah, I'm available. Yeah, no worries.
Okay, sounds good. So we have a question from Amrit. Is the master plant BU1 model plus the REX4 BU1 suitable for controlling a solar plus BESS hybrid facility where the net injection at the POI is limited to the solar megawatts, or the plant megawatt injection output is more than the solar watt megawatts, but less than the summation of the solar plus BESS MVA ratings?
Yeah, I get what Amrit is trying to say. Okay, so answer is yes and a no. Yes, if you're allowed to change the model parameters, because then you can limit the megawatt injection from both the facilities, either the solar or the BESS. But some, regions, they will not allow you to change parameters, because they will say, okay, these are the site specific parameters and these are the ones that cannot be changed. In that case, you would your model should be good enough to dynamically adjust itself, because it can so happen that you would want response from a solar to be curtailed, and then you want the rest from the BESS. So in that case, the state of the charge of the BESS becomes very important. So in that case, your PLNT-BU1 is not a good example because it dynamically cannot change the megawatt based on the parameters available. In that case, you'll have to write a user-defined model.
Okay, we got another question from Mandava. Do you match the simulation results to the field tests or to that of the OEM provided information?
So I'm not very sure on what Mandava is mentioning regarding OEM provided information, but to the first point, the plots that I've shown in the slides, these are actual projects and actual test data. So we match the simulation data result to the test data. I'm not sure what you mean by OEM provided information, but to answer the first part of your questions, we match the simulation models to the test data, which is the actual data in the field.
Okay, so are there any more questions here before we let Tamarjit go here? All right, so it looks like there's a lot of interest, a lot of really good questions here for Tamarjit. Again, Seagray Canada NGN Network would like to, thank you, Tamarjit, for again taking the time out of your
Thanks.
day for providing all this really interesting information and material. So this is really great in this new, power system field where we have this integration of inverter and renewables. It's going to be a lot of challenges in the future, and we'd like to thank you so much for taking your time for that. So
thanks, Kasum. Thanks to you for inviting me and having me up.
All right. So again, thank you very much. I'll stop the recording here. And thanks everyone for